Motion contains rich information about the world around us. Even in the absence of detailed spatial information, motion can be enough to identify different actions and even convey complex information about feelings or stories. However, often datasets used for video classification contain classes that can be recognized from a single frame. Therefore, networks may not focus on image information. This makes it difficult to evaluate progress on temporal modeling. We present temporal classes, which are those where temporal information is actually critical to recognize them, like in these examples. We show that temporal classes help evaluate progress in temporal modeling, and training on them has several advantages. We also present the methodology we use to discover these classes. We show the frames of a video shuffled in time to several human annotators and ask whether they can recognize the action class. This allows us to show all spatial information and only remove the motion. We use the kinetics and something datasets. We show the original video in correct order as control and select those classes where the gap between control and shuffled is large. What can time tell that images alone cannot? Some examples of temporal classes in kinetics include dancing classes and skiing styles. In something, temporal classes often involve moving the camera in a particular direction, or opposite classes like covering versus uncovering. For experimentation, we create a second split, which we call the static classes, containing a sample of non-temporal classes of the same size as the temporal set. We measure the relative gain of a network from testing on static classes to temporal classes on several networks. As we plot this relative gain, we observe that networks with higher ability to model temporal information actually gain more when tested on temporal data. This is a sanity check that accuracy on temporal classes are a good measure. We now use the temporal classes as a benchmark. We test a suite of commonly used networks. If we were to consider only the accuracy on the temporal dataset, larger networks with more capacity would always do better than the lightweight ones. Instead, we consider both the actual accuracy on the temporal classes and the relative gain described before. We plot the results in a 2D graph. The top models will be in the top right corner of the graph. We observe that using flow unsurprisingly always helps, as the triangles in the graph have higher performance. We also observe that I3D struggles more than R2 plus 1D and R3D, which shows a bias towards image information. This could be due to the training process, where temporal filters are inflated from spatial filters learned from ImageNet. We measure the effect of training on temporal classes. We test on the videos shuffled and observe that the performance drop is larger when training on temporal classes. This shows that training on temporal data actually helps learn more sensitive temporal representations, since shuffling affects performance more. We also split the sets on seen and unseen classes. We observe that training on temporal classes performs much better on unseen temporal classes. This suggests that training on temporal data avoids image bias and generalizes better. For more details and the annotation of the classes, please refer to the paper. Thanks for watching.